Hello, for those that are just joining us on YouTube. And it looked like there was a question flashing up, and then my screen took that question away. There we go. So this week, everybody is watching the videos every 11 o'clock for lecture. And when we do get back into the campus next week, assuming that we do, we'll pick up lecture based on where online lecture finishes on Friday this week. So regardless of which section, everybody's been prevented from going to lecture this week on campus. So follow the lectures this week, Monday through Friday, and wherever we finish on Friday, that's where I'll be picking things up again with everybody next week. Okay. If we are on campus, you'll definitely be coming to lab. Lab for the foreseeable future, until you hear something else, is always going to be on campus. This week, of course, nobody's allowed on campus this week. So just follow the Zoom meeting connection, which will appear about 20 minutes before your lab time starts. And we'll just do some practice exams this week. The exam, I still want everybody to do the exam this week. I'll set up multiple times, and then we can negotiate with people if they still can't take the exam this week. Okay. Right, we are recording. Just double check that. It's not been a smooth 24 hours. Okay, we're recording. Again, so this is the Tuesday lecture. Yesterday's lecture will appear later on this afternoon once I sit down and just redo the whole thing. Okay, so we had finished yesterday talking about significant figures. And we had said for significant figures that any non-zero number is always significant, like the 9, the 2, the 8, the 4, 7, and 3, etc. And the only problem comes with the zeros in the number. Okay, another question coming in. First exam is not up and connect. First exam was not due to start to Wednesday. This is only Tuesday, so no exam yet. The exam will probably not appear now till Thursday because we've pushed back the polling questions, which were going to finish tonight. They are pushed back to Wednesday night. The homework, which was supposed to finish on Wednesday night, is now pushed back to Thursday night. So people can take the exam early on Thursday or take it on Friday. That's the 2 days I have planned for the exam. So the only tricky part with a number and its number of significant figures is the zeros in the number. They've fell down into 3 categories. These zeros in red, the zeros at the beginning of a number, before we've seen a non-zero digit like a 9, as we read from left to right. Those zeros in red are never significant because we may have gone past the maximum capacity of the machine to measure data. Just like a set of bathroom scales, there's a limit to how much mass they can measure. Zeros in the middle, which are surrounded by non-zero numbers, are always significant. There's real data to the left, there's real data to the right, so this must be a real measurement of data too. And then the zeros at the end, we only include zeros at the end in blue if there's a decimal point in the number somewhere. Could be further to the left or further to the right, but as long as it's there somewhere, we will include zeros at the end. So never, always, and only if there's a decimal point. So that gives us the values of 3 significant figures, 2 significant figures, 4 significant figures, 4 significant figures, 1 significant figure, 2 significant figures, 3 significant figures, and then finally 4 significant figures. We never count zeros at the beginning, even if there is a decimal point. We only care about the decimal point for zeros at the end of the number. Okay, so on to the new bit, I think, is to think about crunching this data down in calculations. Now, it depends on the kind of calculation that we're doing. And so if it's a multiplication or a division, then we want the final answer to reflect the minimum level of precision, the minimum level of confidence, because you're often taking this data from different machines. So the machine which gives out a number with the least number of significant figures is the machine and the value that we have the least confidence in. So we've got a value with 5 significant figures and another one with just 3 significant figures, and we have to multiply them together. So our final answer is only taken to 3 significant figures, that minimum confidence. A value with 2 significant figures, another value with 3 significant figures. Our confidence for the final answer is only as good as that minimum level of confidence, the 2 significant figures we saw from the first number. Then 3 significant figures compared to 2, so a final answer that only has 2 significant figures. 3 significant figures compared to 3 significant figures, so a final answer to 3 significant figures. However, when we're doing addition and subtraction, for some weird reason, which I've never been able to understand, scientific community decided to do something a little bit different. Instead of counting significant figures, we count the number of decimal places in each number, and we'll quote a final answer to that minimum number of decimal places. So 1 decimal place compared to 3, so we'll quote a final answer to just 1 decimal place. 2 decimal places compared to 3 decimal places, so we'll quote the final answer to just 2 decimal places, dp. Not sure why that is, other than scientists and chemists just loving to be jerks. That's probably the real reason. If we look at a couple of extra examples, let's see, so 16 multiplied by 12 divided by 3, we've got 4 significant figures here, another 4, but then there's only 3 significant figures here. We'll perform the calculation from left to right without worrying about significant figures. Just do it all on your calculator, the full thing. And when you get the final answer, then when you have that final answer, then adjust to the appropriate number of significant figures. And so the final answer actually comes out as exactly 64. But your answer is supposed to be to 3 significant figures, so you have to add in that 0.0 to give the 3 significant figures. Final answer should always reflect that minimum level of precision, even if you have to kind of create it. So it's just telling us when we look at that data compared to other values and other calculations, we've got that level of confidence in the answer, 3 significant figures, which we might later compare to data where there's only 1 or 2 significant figures. So we can say, aha, that's the value to work with. Next one, 12.5 multiplied by 16 divided by 8.005. So 3 significant figures, 3 significant figures, then 4 significant figures. We again, just from left to right, continue the calculation. Only reason you wouldn't do it from left to right would be if there was an appearance of parentheses somewhere in the calculation. So for example, if something like this was apparent, you then do this bit first. Always do parentheses first. Otherwise, as in this case, which doesn't have any parentheses, just start on the left and crunch through to the right. Now, with more complex calculations, where there's maybe subtraction, addition, and multiplication, then things start to get more complicated, but we are just not going there. Okay, excuse me. I do apologize. My breakfast trying to attack me there. Excuse me. We'll never mix up multiplying and dividing with addition and subtraction. That's a special set of rules called PEMDAS that some of you might be aware of if you've taken a higher level math course, but we're just not going to go there. So there's our raw answer for this one. And of course, we wanted our final answer to be just 3 significant figures. And so we're going to keep that part. There we go. And the first figure to be dropped is the 8. Because it's 5 or greater, we're going to round up to 25.0. Don't forget to put the 0 in because it's supposed to be 3 significant figures. Next one, subtraction and addition, just from left to right, unless there's some parentheses in there. And so we get a raw answer of 1.06. We check on the level of precision we should be using, and that was 1 decimal place from that last number. And so the cutoff is here, but because it's 5 or greater, we're going to round up to 1.1. So that's a general rule when we have to chop the number into a particular or appropriate number of significant figures or decimal places. We look at that first digit, which is for the drop, and ask ourselves if it's 0 or up to 4 or 5 up to 9. If it's 4 or less, then we're just going to round down. If it's 5 or more, then we're going to round up. Here's some extra examples trying to show that point. So looking at all of these numbers and trying to just cut them down to just 3 significant figures each time. For the ones which are less than 5, for the first number to be dropped, so 4 or less. So we've got an example here, the 0.0029825, keeping it to 3 significant figures. It's a 2, which is the first number that would be dropped. And so because it's 4 or less than 5, we just round down. And so we just erase that part of the number, which leaves us with 0.00298. Likewise, the one on the end here, that's the part, there we go, that's the part of the number that we want to keep. And the first digit for the drop is less than 5, so we'll just erase that part of the number, and it leaves us with 1.94. Sometimes the first number to be dropped is 5 or greater. And so, for example, keeping the 22.4, first number to be dropped is a 9. So we erase that and round up to 22.5. The 4.00 is what we initially want to keep, but the first number to be dropped is 5 or greater, it's 9, so we're going to erase that and then round up to 4.01. And then the next one is a little bit trickier. We want to keep 3 significant figures, but the first number to be dropped is a 5, so 5 or greater, we're going to round up. So in theory, it should be just 552. However, we have lost the magnitude of the number. 552 is very different from 551,533. That's a completely different number because of the magnitude loss. So if we're being pushed to cut it down to 3 significant figures, but we don't want to lose the magnitude, we can use the scientific notation that we talked about yesterday. And just for people who maybe weren't here yesterday, for that lecture, it still has to be put back in. We imagine the real number as being a number between 1 and 10. So instead of the decimal point being there for 551,533, we imagine the number as being a number with a decimal point there, 5.51533. And so as we look at it, we've actually moved the decimal point once, twice, 3 times, 4, 5 times to the left. So the real number has 5 orders of magnitude on that 3 significant figure number that we're trying to use, 552. So we use a scientific notation, 5.52 rounded up as we intended to, times 10 to the power of 5. It's basically the 5.52 times 10 times 10 times 10 times 10 times 10, 10 to the power of 5, as we talked about yesterday. And also look out for a knock-on effect with significant figures, as I think we talked about the other day on the question of the day. So a number like this, which had to be cut to 3 significant figures, the first digit to be dropped is a 9, so we'd have to round up. But we round up the next digit, that means we'd have to round up the next digit, which means we'd have to round up the next digit. So there's sometimes a domino knock-on effect. And so 3 significant figures, it would actually be 7.00. So if you're rounding up to the next digit and it's already a 9, that's going to cause a rounding up and a knock-on effect as well. Okay, there's some extra examples. Take a couple of minutes and we'll use this for a break actually. Take a couple of minutes and, excuse me, give those a try. 7.01 times 8.1, 102.4 divided by 31.7, 90.002 plus 12.6, and 8.55 minus 2.1 plus 5. So take a couple of minutes and give those a try, or you can use that to take a bathroom break and get a drink, or check in your wild feral kids. Let's take a look at these ones. So first, just always a good start to just work out the raw answer and then worry about significant figures or decimal places. That's 7.01 times the 8.1. The raw answer comes out as 56.781. And we want that final answer to be to just 2 significant figures because of the 8.1. So we're going to keep those 2 figures. The first number to be given the chop is going to be the 7. That's 5 or greater, so we're going to round up to give a final answer of 57. Final answer, 57. Second one, 102.4 divided by the 31.7. Raw answer for this one, quite a long one, 3.2302839 for its entirety. We've got 4 significant figures compared to just 3 significant figures. We want 3 significant figures for the final answer. The first digit to be dropped is a 0, so that's just a case of rounding down. So 3.23 for the final answer. Next one, now we have to change tack because we've got an addition. And when it comes to addition, we're only looking at the number of decimal places. 90.002 plus the 12.6. Final raw answer is 102. 0.602. We've got 3 decimal places compared to just 1 decimal place. So the final answer should have just 1 decimal place. First digit to be dropped is a 0. And so we'll just forget all about the 0 and the 2 and leave it as 102.6. Okay. Last one, 8.55 minus 2.1, then plus 5 comes to 11.45. And so we've got 2 decimal places, 1 decimal place, and then none. So our final answer shouldn't have any decimal places. First number to be dropped is 4, which is less than 5. So we're just going to erase that and round it down to 11 in this case. So always be wary. If it's multiplication or division, we're looking for the least number of significant figures. But if it's addition or subtraction, we're just looking for the least number of decimal places. And a question, if our operation has both multiplication, division, addition, and subtraction, but different significant figures, decimal places, do we pick the lower number or either significant figures or decimals? So basically, for one thing, you have to think about which parts of the calculation are priority, and multiplication and division are more important than subtraction or addition. So you'll do those parts first. And normally the idea is just to do the raw number or the raw numbers all the way through the calculation. Then when you get to the end, then look for what the limiting factor is in terms of the least number of significant figures or decimal places. But again, that's going fully into what we call PEMDAS, which is P for parenthesis, E for, I think that stands for exponential, and then division, etc., multiplication. There's a real hierarchy of how you handle a real multiple layered calculation like that, but we are not going to cross the streams, so to speak. Our calculations will be a mixture of addition or subtraction, or a mixture of multiplication and division, but we're not going to get into the nitty-gritty details that PEMDAS has because it's just too advanced for this level of course. The only thing that we might do sometimes is just have a multi-barreled calculation, and maybe there would be some parentheses to tell you to do that particular part of the calculation first. If the parentheses are not there, you can just assume to do it from left to right. So Victor is trying to get us into the really, really tricky ones. Like for example, it could be something like 5 plus 7 minus 2 times 14. So you've got something like this, you would do that part first because multiplication is a higher order than addition or subtraction. Then when you've got an answer for that, then you could do the rest of the calculation just as you read it from left to right. So again, we're definitely going to keep a lid on the complexity for these ones. I mean, those trickier examples do exist, but it's important to point out that we're not going there because that's beyond the scope of the course, okay? We're giving people a taste of this kind of stuff. Now, we need to just briefly talk about exact numbers and numbers which have uncertainty in them. With an exact number, it's a specific count of objects or things. So for example, you might have 3 marbles. There's no uncertainty in that. It's definitely just 1, 2, 3 marbles. It's not slightly more or slightly less. It's exactly 3. or 5 syringes, or 5 pain-killing tablets. It's an exact amount. It's what we call an exact number. Also, when you're doing a metric conversion, that conversion is considered to be an exact number as well. And so we don't think of these exact numbers as having any limitation in their accuracy. So if you have some kind of calculation to perform with multiple numbers, the exact numbers are not your source of uncertainty. So for example, you might be calculating the radius of some object, and you'll have to measure the diameter from one side to the other of that object, and then divide by 2. Now that measurement of the diameter will have to use a ruler. And measurements with a ruler, measurements which use your eye, like this, have a certain degree of uncertainty. And they will be the source of limitation in the accuracy of the calculation. So you'll need to work out how many significant figures are in that number, and then your final answer should be quoted to that minimum level of significance. Even though 2 is just one single figure, one significant figure, you assume that it's an exact number and has an unlimited number of significant figures. So you're effectively taking the diameter and dividing it by 2.000000. It's got an infinite number of significant figures associated with it. Oh, yes, baby, what? Right, sorry about that. Where were we? My daughter just putting in a request for more mermaid egg toys. That's her thing just now, mermaids. So you can buy eggs where little toy mermaids will hatch out of them. So she's put in a request for more. All that kind of important stuff. Anyway, so there are exact numbers with specific numbers of objects, but there are inexact numbers or numbers which carry a certain amount of baggage, a certain amount of uncertainty with them. We sometimes refer to as inexact values. And it's really just measuring anything with your eye. So for example, a ruler measuring the length of a paperclip, the degree of accuracy can depend on the degree of accuracy with the ruler that you're using. For example, here we've got the paperclip and it measures at least 2 centimeters, but not quite 3 centimeters. So there's a degree of uncertainty here because we're not quite sure how long this length is. So with these uncertain values, you're always going to have to estimate the next significant figure. So we know it's 2 something, and to my eye, it looks about a third of the way along to the 3 marking. So I would estimate that as 0.3. And so our value becomes 2.3. But there's uncertainty tied into that measurement because we don't really know what that length there is. We could use a more accurate ruler, one which has millimeter markings, but we're never going to get away from the fact that there's a degree of uncertainty in the number. So for example, 2 centimeters again, and we see we go along 1, 2, 3 millimeter markings, but it's somewhere. Excuse me a second. I just want to do 5 more minutes. Bear with me, guys. All right, it's just one of those days. Okay, so where were we? Oh, yes. So even if we use a more accurate ruler, we can see that we've got 2.3 centimeters, as I had predicted in the first one, but there's still a degree of uncertainty because the end of the paperclip is in between the third and the fourth marking. So it's 2.3 something, but not as much as 2.4. So the best I can estimate it, I take that as being slightly less than halfway. So I've estimated that as 2.34. So the 4 is the uncertainty bit. That's the bit that you're just going to have to guess. And with any eye measurements like this, which are not exact values like 3 pebbles or 4 eggs, when you're doing a visual measurement like this, which isn't an exact value because it's a discrete number of objects, you're always going to have a certain amount of uncertainty. And you're going to have to make your best guess for that. We see it in measuring volumes as well. So because of, excuse me, she's just very excited because she pooped in the potty. Okay. So if we look at a measurement, she's in a minute. Give me 5 minutes. Right, I think we're just going to have to try and get through this last 5 minutes. I'm getting very anxious for lunch. So let's say you've got a measurement in, let's see if I'll shut the door, maybe they'll forget where I am. We've got this measurement in the measuring cylinder. You'll notice the forces of adhesion to the sides of the glass. So the measuring is always at the lowest point of the curve. And we can see that we've got clearly 6 milliliters. We don't go as high as 7, but we do have these graduations for 0.1 of a milliliter. So we go 1, 2, 3, 4, 5, 6. So it looks as if it's exactly 6.6 milliliters. However, you're still estimating that it's exactly on 6.6, and you've still got to clarify that level of uncertainty. So because you think it's exactly on 0.6, your estimation is that the next significant figure will be 0. You're clarifying that you think it is dead on 6.6 by adding in the 0. Next one, we've got 2.12345 and a little bit more this time between the next two graduation marks. So 2.6 for sure, and it looks like it's halfway, so 2.65. So with these visual measurements, you're always estimating that last significant figure, unless it's a discrete number of objects. Who knew children could make so much noise? Okay. Let's see. I guess that's probably a good place to stop because there's just so much mayhem here. I do apologize about that there. It's just getting close to lunch and I'm getting excited. So, oh dear. We'll finish there and we will get the chapter finished off tomorrow, density. Okay. And within a couple of hours, we should see yesterday's lecture up on YouTube as well. Okay. But I'll probably put today's lecture up on YouTube first. Okay, guys. I will talk to everybody soon. Bye.